In this video, we have a nice diagram here of a triangular plot of land, 400 feet wide and 200 feet tall, and then it's cut by this hypotenuse. And we've got some area, 15,000 square feet, rectangular, that needs to be built inside there. And the question is, what should the dimensions of this rectangle be so that the square footage is 15,000 square feet, and this corner has to touch the hypotenuse. So what we're going to do is use Euclid's theorem, and that has to do with similar triangles. So when we make this rectangle, we're going to cut this larger triangle off, and we're going to make two similar triangles. So the red and the blue triangles are similar, meaning they are not the same size necessarily, but the angles are all the same. So all of this angle is the same as this angle, and then we've got this angle and this angle are the same, and this angle down here is the same as this. Of course, those are the 90-degree angles. So those are similar triangles. We're going to use that. Now, Euclid's theorem says that the side lengths, say A over A prime, that's the similar triangle's length of A, equals one triangle's length B over the similar triangle's length B, which also equals the length C over the similar triangle's length C. Okay, so we're going to use that. We're only going to use two of the side lengths, but that will help us. That'll get us to what we need. So first we need to label this stuff. I'm going to label the height of the rectangle X. I could label it A and B, but we're just more familiar with using X and Y. So I'll use X and Y. I will label the length of the rectangle as Y. Okay, now what we have left here, I'll write this in red, this distance of this triangle. Now that's going to be the 200 feet total minus this little x. So 200 minus x. I won't label it feet there just to save us some room. Down here, this length of this triangle leg is going to be the 400 feet total minus the y that is cut out from this rectangle. Okay, we're getting somewhere. Now let's take a look at the lengths of the other legs of the triangles. Well, of course, this is going to be y up here. It's just the same as this length here. So I've got that length y for this triangle. And we have this length here is just going to be x. Let's not put it there. Let's put it here. Okay. So let's make our proportions here. So I have this length, 200 minus x. I'll write that in red. I'll try to keep this color coded. 200 minus x over this length of just x equals this length of y over this length, and that is I'll put that in blue. That's this, 400 minus y. Okay, so we have what we need there. One of the formulas, or one of the equations. But this is two unknowns, x and y still. Well, we do know this. X times y, length times width, equals the area. So let's just write that. X times y equals the area, that's 15,000 square feet. Okay, now that's really going to get you far. Right now you can uh, go ahead and solve. And setting that up is usually the tough part. But let's go ahead and just run through some of the basics of solving this. We're going to solve for y, and so we get y equals 15,000 divided by x, and then I'm going to take that and plug it in every time I see a y in this, I'll call it the master equation. So let's do that, and I'll just do this in black here. So I'll write that out, and that's what we get. Notice that I have substituted 15,000 over x every time I saw a y in this master equation. Now we can run through and multiply everything in this large complex fraction by x, and that's just going to clear out some of the fractions within this fraction. And at this point, what I'm going to do is then cross multiply. And notice that I'm multiplying this entire expression, 200 minus x times 400x minus 15,000. And just to break convention here, I am going to skip ahead a couple of steps while I do that. That is the result that we get after we cross multiply. And let's factor out or divide out some stuff to make these smaller numbers that we can, and clean it up a little bit. And what I did there was I subtracted 15,000x from each side, and then I divided through by negative 400. So that makes this much more manageable. And now we can actually factor this one. If we couldn't factor it, of course, we could just use a quadratic formula or a calculator. If we had a calculator handy, we would have solved that, used the calculator from the beginning to solve this instead of trying to simplify it. But this is just great. X minus 150 times x minus 50 equals 0. So that gives two solutions. X equals 50 or x equals 150. A lot of times in problems like this with a quadratic, you have to cancel, you have to throw a solution out because it doesn't make any sense. But here we have two possible solutions. Well, those are not the dimensions. It's not 50 times 150. Remember, we have just solved possible values of x, and we need x and y. So let's see what happens. I'm going to scroll this down just a little bit so we have some room. So we can either say that x equals 50, and then what would y have to be to equal 15,000? And if x is 50 feet, then y would have to equal 300 feet. So that's one possible dimensions of this rectangle. Or we could say that x is 150 feet, and we could let y equal then 100 feet. And we would also get an area of 15,000 square feet, and the rectangle would hit the corner right there on the hypotenuse of the larger triangle. So this would all work. That was a nice problem.